This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy, we go deep and lightly surface the big ideas.
Welcome back to the Deep Dive. If you're tracking explosive evolution of artificial intelligence, the models that are writing complex code, generating stunning images, passing doctoral level exams, you might assume that the fundamental architecture that underpins all of this power is constantly shifting. That like every few months, some radical brand new design is released.
And that assumption, well, it would be mostly wrong.
Right.
The deepest, most powerful AI models, especially the large language models we all rely on today, they still operate on a foundational architectural trick that is, believe it or not, nearly a decade old.
It's true. We're talking about the residual connection component introduced way back in 2016. It's what keeps these incredibly deep neural networks from just collapsing into noise. Think of it as the core stability mechanism, maybe like the ultimate express lane for information inside the machine. Without it, the signal just dies before it can get to the end.
Or, on the flip side, it explodes into a completely unintelligible mess. It is, and really has been, the architectural anchor of modern deep learning.
But the relentless pursuit of complexity and capability, that drive to make networks wider, deeper, more powerful, it meant that researchers eventually had to challenge that anchor.
They had to. And when they tried to make that simple, stable connection more complex, to give the model vastly more capacity for internal information exchange, they immediately ran into a numerical crisis.
What crisis?
A catastrophic failure of stability that threatened to completely derail the scaling of large language models.
So today, we are deep diving into the story of that crisis. And it's really ingenious solution, as chronicled by the DeepSeek AI research team, led by Zen2C, in their paper MHC Manifold Constrained Hyperconnections.
It's a fantastic story.
It really is. This is a fascinating journey that takes us from an architectural dead end to this beautiful mathematical rescue and ultimately to the stable foundation that you need for training these leviathans like this 671 billion parameter DeepSeek V3 model.
Our mission today is to understand the core trade-off they faced. How do you inject massive complexity and expressive power into a network without sacrificing that fundamental stability that the simple residual connection gives you?
Exactly.
And the answer, as we're going to see, wasn't about adding more complexity. It was about applying a precise external geometric constraint to harness the chaos.
Okay, let's unpack this journey. And we have to start with the bedrock principle they had to protect, that sacred rule of the residual connection. So to understand why the solution, this MHC, is so profound, we have to start with that foundational element, the standard residual connection, or ResNet. For a long time, the holy grail in neural network architecture was just depth.
Just go deeper.
Right. If a network was deeper, it should theoretically be more capable.
Exactly. But as networks got deeper in the early 2010s, they failed. They failed spectacularly. Information entering the first layer would essentially just dissolve by the time it reached the last layer.
Yeah.
Or the gradient signals you used to train the network would vanish entirely. That's what the Hidial paper from 2016 solved.
And the mechanism is, well, it's deceptively simple. We represent the output of layer $1 as the input $6 plus the result of the main function find dollar applied to that input.
So mathematically, it's just $SDR plus 1 plus FXL The input $6 gets a free pass. It just skips ahead, totally unimpeded.
And that little $6 term, that direct bypass, that's called the identity mapping.
And this property is absolutely crucial because it ensures signal continuity. If you imagine stacking hundreds of these layers together, the signal that starts at a shallow layer, $6, it maps directly to any deeper layer, $6 through this continuous path without ever being fully modified or diluted by all the computations in between.
So if the network is, say, 100 layers deep, which is pretty standard now, the signal from layer 1 can actually reach layer 100 without vanishing. But why is maintaining that signal flow so critical for the training itself?
It comes down to backpropagation. That's how the network learns. During backpropagation, the training signal, which is the gradient, travels backward through the network.
Okay.
If the connection preserves this identity mapping, the average intensity of that signal stays constant. This is what prevents the gradients from either exploding into uncontrollable noise or vanishing into useless zeros.
So if you lose that stability, the network literally cannot learn effectively at a massive scale.
You can't. It's the absolute precondition for training deep models efficiently.
Now, this architectural foundation, the transformer built on the ResNet block, it naturally led research in two pretty distinct directions.
Yeah, we saw research split into what we call micro-design and macro-design. Micro-design is all about refining the internal components, optimizing the attention mechanisms, making the feed-forward networks more efficient, things like that.
And macro design. That's the bigger picture, the topology.
That's defining how all the computational blocks are actually wired together. Historically, people tried these really complex structures like DenseNet or FractalNet, which dramatically increased connectivity.
Right.
But more recently, the focus in macro design has shifted to expanding the expressivity of the existing residual stream itself. So instead of connecting layers more densely, they wanted to give the signal stream more internal bandwidth.
This shift aligns perfectly with the DeepSeek AI philosophy, which is really important context here. They operate under a strategy they call HPC co-design.
Right. HPC co-design is this understanding that you can't separate model innovation from infrastructure innovation. Refining the mathematical architecture, like MHC, has to happen at the same time as optimizing the underlying infrastructure. The specialized kernels, the parallel processing schedules, the GPU efficiency.
So they realized that to train these massive models both economically and stably, you need breakthroughs in both software and hardware design together.
Simultaneously.
And this brings us right to their architectural gambit. The hyperconnections, HC architecture, which was their first really ambitious attempt to increase that residual stream bandwidth.
HC was radical. Instead of just one residual stream, it introduced a non-stream residual design. And they typically used 4 parallel feature streams, so one $4 resin.
So now you have 4 simultaneous highways for information traveling through the network, layer by layer.
But the real innovation wasn't just having 4 streams. It was how they allowed those streams to, talk to each other.
Oh, okay.
Precisely. They added these learnable matrices, which they called H-is, and these modulate the connection strengths among the parallel feature streams. This allows for this complex, rich information exchange internally between the 4 streams at every single layer.
So instead of 4 independent streams, you have a single unified 4-lane highway where cars are constantly merging, communicating, and exchanging passengers, all controlled by this learned matrix.
That's a great analogy. The whole intention was to dramatically increase the topological complexity and, therefore, the capacity for internal information exchange.
Without increasing the computational cost, the FLOPs of the individual units, like the attention block or the FFN.
Exactly. They managed to decouple the model's capacity for representation from its core computational burden.
And the initial results showed this was a winning idea. The paper talks about ablation studies showing that while they needed some matrix mappings for, dimensional consistency, the internal residual mapping yielded the most significant performance gain.
And this is the crucial point for our narrative. It confirmed that the model truly benefited from this rich, decentralized communication.
Right.
Think of it like a large project team. If every department only reports to one single bottleneck manager, that's the traditional ResNet stream complexity and nuanced data get lost. But if you allow decentralized peer-to-peer communication between 4 subteams, the overall intelligence and speed of problem solving, the model's expressive power, it just skyrockets. HTC proved that this internal cross-stream mixing was vital for performance.
But that newfound freedom, that amazing capacity for communication, it came at a price that almost bankrupted the entire system.
The story of HC is a classic reminder that in deep learning, performance and stability are often 2 sides of the same coin, and they're usually locked in this constant conflict.
So HCC increased performance.
But it fundamentally compromised the identity mapping, that sacred stability mechanism we just discussed.
So the very matrix that delivered those huge performance gains was the culprit. How did an unconstrained learned matrix break that stability rule?
It boils down to conservation. We established that the traditional ResNet works because that signal $6 is passed forward untouched. That ensures the global mean of the features is conserved across layers. The unconstrained nature of the learned dollars meant that when the signal passed through it, the feature mean was, it was no longer guaranteed to be preserved.
Why is preserving the mean so mathematically important? I'm guessing if the mean starts to shift wildly, the features themselves, the machine's understanding of the data just become unpredictable.
That's exactly it. When you lose feature mean conservation, you're introducing bias into the feature stream, layer after layer after layer.
A compounding error.
Right. So when you compose these layers, when you look at the signal flow from layer dollars to a very deep layer to dollar, which involves multiplying this composite mapping, prod each day, this lack of conservation leads to runaway growth. The signal magnitude is prone to either unbounded amplification or attenuation.
So we're back to the architectural death sentence. If it attenuates, the signal vanishes. If it amplifies unboundedly, we have that gradient explosion that just leads to numerical disaster.
The system is consuming itself. That unimpeded, stable signal flow, the core premise of residual learning, was completely undermined by the HC architecture when they tried to scale it up. HC had given the network massive freedom, but the network immediately used that freedom to destroy itself.
The empirical evidence of this dead end is really compelling, and it's what forced the DeepSeek team to pivot. Tell us about that 27 billion parameter model experiment.
So they were monitoring the training stability. And figure 2 in the paper just clearly illustrates the crisis point. The HE implementation exhibited a dramatic and totally unexpected loss surge around the 12,000 training step.
A surge.
Yeah, while the baseline model continued to learn smoothly, the HE model's loss suddenly spiked toward infinity. They hit a wall.
That moment must have been terrifying for the engineers.
Yeah.
A loss surge signals that the model isn't learning anymore, it's diverging. And this divergence was directly correlated with what they saw in the gradient norm.
Right. The gradient norm, which is the measure of the signal strength used to update the weights, also became catastrophically unstable. But the most shocking finding really came from analyzing the signal propagation itself.
What did they find?
When they calculated the gain magnitude of that composite mapping across layers in the HC model, the gain magnitudes reached nearly $105.
A gain of $105. That's 5 orders of magnitude. So if a signal goes into one layer and it's multiplied by a factor of 100,000 before it reaches the end of the network, that's not an information flow, that's a nuclear reaction.
It's architectural chaos, you put it well. The system was actively screaming itself to death. The signal just exploded dramatically across the layers, rendering training completely impossible beyond that critical point.
So the high capacity delivered the performance gains, but it sacrificed the stability they needed for large-scale production model.
It did. And yet they couldn't just throw away the HC idea because it had proven its value. It decoupled capacity from FLOPs.
Right, they had established that the rich topological complexity was key.
Exactly, but the failure wasn't just mathematical, it was also practical, which brought them right back to their HPC co-design philosophy. Even if they had managed stability, the efficiency problem was still there.
The memory access overhead.
Yes. The expanded residual stream with those and 4 Thor streams, it dramatically increased the overall memory footprint. Moving those widened feature vectors in and out of GPU memory constantly creates this massive memory bandwidth bottleneck.
So the original HC design had focused purely on the computation and just ignored the hardware reality.
Totally unaddressed. So HC failed on 2 fronts of scalability. Numerical instability because of the broken math, and practical inefficiency because of unaddressed hardware bottlenecks.
They were stuck. They needed the complexity of our brains, but they required this strict, self-imposed mathematical control to tame it. They needed a golden cage for their architectural beasts.
That's a perfect way to put it.
This marks the brilliant turning point in the paper. The DeepSeek team, they couldn't just revert to the simple identity matrix, IAHU, because that would kill all the performance gains.
Right.
So they needed a way to restore the stability of the ResNet identity mapping while keeping the performance-boosting complexity of the learned matrix H.
And they realized the solution wasn't in reforming the matrix itself, but in constraining the space in which the matrix could exist. This is the core concept of MHC manifold-constrained hyperconnections.
Okay, let's break down that term manifold. For our listeners, we often hear this term in, like, topology or geometry. How should we visualize a manifold in the context of an AI parameter space?
Okay, imagine the entire universe of possible values that the least matrix could contain. That's a high-dimensional, totally open space. The catastrophic instability meant that the training process was allowed to explore these really dangerous, explosive regions of that space. A manifold is essentially a specific, precisely defined surface or a boundary within that high-dimensional space. By projecting the matrix onto a manifold, you force the training process to only use matrices that fall within this defined, mathematically safe region.
So it's the opposite of chaos. It's imposing geometric order. So what specific manifold did they choose, and why did it restore that conservation property?
This is the mathematical breakthrough. They constrained the layer matrix to be a doubly stochastic matrix. This choice of constraint directly addresses the stability crisis.
Doubly stochastic. That sounds highly technical. Can you explain that in terms of, like, balancing?
Absolutely. Think of the layer matrix as a ledger of connections and weights between your four parallel streams. The constraint demands two things. First, that every row must sum exactly to 1, and second, that every column must also sum exactly to 1.
So if you look at the matrix horizontally, the total output weight from any one stream to all the others has to be 1. And if you look vertically, the total input weight coming into any one stream from all the others is also 1. It's a perfect balancing act.
That's the conservation principle at work. When you multiply a feature vector by a matrix that has this property, the resulting operation is a convex combination of the input features. This is the mathematical safety mechanism.
So why is a convex combination inherently safe compared to the unconstrained operation that gave them that 105.5 gain?
Because a convex combination ensures two things. First, since all the weights are normalized to sum to 1, it strictly regularizes the signal norm. It prevents the values from becoming unboundedly large. You can't just create mass out of nowhere.
Okay.
Second, and this is the direct fix for the ResNet crisis, it conserves the feature mean. If the feature mean is conserved layer to layer, you've successfully reinstated the architectural anchor that ResNet relies on for stability.
Wow. That is incredibly elegant. The DeepSeek team found a mathematical constraint that allows the matrix to still learn complex, rich communication,
Because it can learn any combination of weights as long as they sum to 1.
but prevents it from breaking the fundamental conservation laws of deep learning.
And here's the truly elegant part regarding scale. Remember, the problem with HCC was that composite mapping, the product of many matrices chained together, this stability has to hold for the entire depth of the network.
Right. If the product of 5 stable matrices suddenly becomes unstable, the fix is totally useless.
But due to the closure property of doubly stochastic matrices, the product of any number of doubly stochastic matrices is also a doubly stochastic matrix.
Wow.
This guarantees that the composite mapping across all the layers will retain that mean conservation property, maintaining stability across arbitrary depths. So the stability is mathematically guaranteed no matter how deep DeepSeek v3 is scaled.
It's fascinating how abstract classical mathematics is saving cutting-edge AI. So we know what the constraint is, doubly stochastic, but how do you actually force the network to obey this rule during the chaotic process of training? How do you project a learned matrix onto this safe path?
You use a 57-year-old iterative projection technique called the Sinkhorn-Knopp algorithm, first developed way back in 1967. The desired manifold, that geometric space of all doubly stochastic matrices, is formally known as the Birkhoff polytope.
The Birkhoff polytope. So we're using an algorithm from over half a century ago to force a matrix into a specific, safe geometric shape. How does the Sinkhorn-Knopp algorithm actually work here?
The training process starts by calculating an initial unconstrained layer matrix, which is probably numerically chaotic. The Sinkhorn-Knopp algorithm then iteratively projects this matrix onto the Birkhoff polytope through a process of alternating normalization.
Alternating normalization.
Yes. In the first step, it normalizes the matrix by dividing each row by its current sum. This forces all the row sums to equal 1. But in doing that, it might mess up the column sums.
Ah, okay.
So in the next step, it normalizes the matrix by dividing each column by its current sum, forcing the column sums back to 1. This process is repeated, alternating between row normalization and column normalization, until the matrix converges to a point that is very, very close to being perfectly doubly stochastic.
It sounds like a slow process of continuous self-correction, just forcing the matrix to find its balance point.
Exactly. And here is where that engineering trade-off for HPC co-design comes in. The Sinkhorn-Knopp algorithm, in theory, converges perfectly at infinity. But during large-scale training, you can't wait for infinity.
Right.
So the DeepSeek authors had to figure out how many iterations were enough to guarantee stability without introducing crippling latency.
And what was their practical solution?
They limited the projection to $20 iterations. This gives you an approximate solution to the doubly stochastic constraint, which is fast enough for training.
That's a crucial engineering choice. By limiting it to 20, The gradient gain might deviate a little from the ideal value of 1 because it's only an approximation.
Sure, a tiny bit. But compared to the unbounded divergence of the original HEC design, that small bounded deviation is a massive success.
And the validation results must have been night and day.
Oh, spectacularly so. Remember the crisis point. The unstable HC resulted in maximum signal gain magnitudes reaching nearly $105. After implementing MHC, after forcing the matrix onto the doubly stochastic manifold with 20 iterations of Sinkhorn-Knopp, the maximum signal gain magnitude dropped to approximately 1.6.
From 100,000 down to 1.6, a reduction by over 3 orders of magnitude, purely through imposing geometric control. That completely restores stability.
It does. We can even see the visual difference in the structure of the learned matrices in the paper. The unstable HC matrices show these arbitrary, large, chaotic values. But the MHC matrices, constrained by the algorithm, they look inherently stable and balanced, with row and column sums consistently adhering very closely to 1.
So the result is total training stability.
Total training stability, allowing them to achieve better convergence and an absolute loss reduction compared to the baseline. The trade-off was solved. They kept the complexity, but tamed the chaos.
This success story of MHC is more than just an architectural fix, isn't it? It validates the entire philosophy of HPC code design. The DeepSeek team solved a theoretical crisis, and then they rigorously optimized the system around that fix to ensure practical economic scalability.
That's the key. MHC not only restored stability, but it delivered comprehensive performance improvements that confirmed the value of the hyperconnection topology.
Let's put some numbers on that success. How did the constrained MHC perform against the baseline and the unstable HC?
The MHC model, especially the 27 billion parameter version, consistently outperformed both the baseline and the HC version on a really wide array of downstream benchmarks. It proved that the constrained complexity provided real expressive power.
For example,
On complex reasoning tasks, for example, MHC delivered a 2.1% performance gain on BBH. That's a crucial benchmark for challenging big bench tasks, and a 2.3% gain on DROP, which requires reading comprehension and complex numerical reasoning over documents.
so this wasn't just a minor tweak. It was a fundamental enhancement to the model's ability to reason and handle complex data. And the scaling experiments confirm this, held up across different sizes.
Yeah, from 3 billion to 27 billion parameters and across different token counts, a robust, scalable design element was achieved.
But now we have to address that practical flaw of the original HCC design. The huge memory access overhead from the expanded 4-stream residual design. The theoretical breakthrough is useless if the system can't run it efficiently.
And that's where the co-design comes in. The DeepSeek team reported that MHC introduced only a marginal training overhead of 6.7%, with one individual $4. That's an astonishingly low cost for such a dramatic architectural improvement.
Okay, so how did they use HPC co-design to get that efficiency?
They used 4 major infrastructure optimization strategies. Let's start with kernel fusion.
And kernels, in this context, are the fundamental computational programs running on the GPU.
Right. And when the GPU executes operations, the latency of moving data in and out of memory, that memory bandwidth bottleneck, is often the biggest cost, not the computation itself.
So what's fusion?
Kernel fusion is the process of consolidating multiple sequential operations, like an RMS norm and then a matrix multiplication, into a single unified compute kernel. Instead of running 3 separate kernels that require 3 separate trips to memory, they do all 3 operations inside one kernel, which dramatically reduces the memory bandwidth bottlenecks.
That's just pure efficiency engineering. They also tackled memory usage head-on by embracing low-precision computation.
That's the second strategy. Mixed precision training, and specifically supporting FP8 mixed precision. Standard training often uses 32-bit floating point numbers. FP8 uses only 8 bits.
Which means a lot less memory.
It drastically accelerates training and reduces GPU memory usage by a factor of 4 compared to 32-bit floats.
But doesn't reducing precision usually introduce instability or, numerical issues?
It absolutely can, which is why DeepSeek's success here is so impressive. Usually, low precision makes stability worse. But because the underlying MHC architecture already guarantees numerical stability and bounded signal gain, thanks to that doubly stochastic manifold, they can safely push the hardware efficiency envelope by using FP8.
The architectural stability enables the system efficiency.
Exactly. And their third strategy directly addressed the memory overhead of the wide enough stream design using recomputing.
Okay, what's recomputing?
The challenge is that during the forward pass, you calculate and store all these intermediate activation maps that you need for calculating the gradients during the backward pass. Storing all of them for a 4-stream, 600-layer network just consumes prohibitive amounts of GPU memory.
So if they can't store them, what do they do?
They just discard them. After the forward pass, the intermediate activations of the MHC kernels are simply thrown away. Then, during the backward pass, they are recomputed on the fly.
Wait, they calculate the entire activation map a second time just to run the backward pass? That sounds like a major computational cost.
It is a trade-off. Computation versus memory. And in modern architectures, memory is often the scarcer resource than computational power, or FLOPs. The recomputing step is localized to specific memory-intensive MHC kernels.
So the slight increase in compute latency is a worthwhile price to pay for mitigating the huge memory overhead.
It allows them to train far bigger models that would otherwise just run out of GPU memory.
And finally, they optimize communication, which is crucial for training a distributed architecture of this scale.
The fourth optimization involves communication overlap, using an extension of their dual-pipe schedule. When training massive models, you split the model across multiple GPUs and even multiple nodes.
Quite parallelism.
Right. And these split models need to constantly communicate gradients and activations back and forth. This communication can leave the GPUs just sitting idle, waiting for data.
So the goal is to keep the computational units busy while the communication is happening in the background.
Exactly. They carefully engineer the dual-pipe schedule to overlap the communication, the PP center-sieve operations, with the computation cycles of the local blocks, like the MLP and attention blocks. This maximizes hardware utilization, ensuring near-full computation communication overlap.
And that dramatically reduces the real-world time and cost of training.
It does.
So the MHC architectural fix is clearly a vital piece, but it's part of a comprehensive engineering masterpiece designed for scale. DeepSeek V3 is a behemoth, 671 billion parameters total, and MHC is just one innovation. Let's look at the other two major architectural bottlenecks they solved.
So DeepSeek V3 is a mixture of experts, MoE architecture. This is why it has 671 billion parameters, but only 37 billion are activated per token. MoE offers enormous capacity at a significantly reduced computational cost during inference.
MoE is great for capacity, but we've seen in other foundational models that it introduces its own stability problem, the routing collapse.
Ah, the routing collapse. This is when the token router gets, well, lazy. It learns to send almost all the tokens to just a few dominant, easy-to-access experts, leaving the majority of the other experts underutilized or completely idle.
So if 90% of your capacity sits dormant, you haven't really scaled capacity, you've just wasted computation.
Exactly.
How did DeepSeek AI solve this stability issue in their MoE layer without relying on the traditional methods?
They pioneered an auxiliary loss-free load balancing strategy. Traditional MoE models fight routing collapse by adding an auxiliary loss term, a mathematical penalty, that explicitly forces experts to share the workload.
But the DeepSeek team found that this auxiliary loss actually degrades the performance.
It does, because it forces the model to prioritize fairness. Even expert utilization over intelligence, sending the token to the best possible expert, it just pollutes the training gradients.
So instead of penalizing the system for being unfair, what do?
They manage expert utilization not through an external loss function, but by adjusting an internal expert-wise bias term in the router. This bias term encourages the router to utilize underutilized experts, but it does so internally without adding complexity or conflict to the primary objective function.
So another parallel stability story. MHC solved the instability in the residual stream, and this strategy solved the instability in the expert routing.
Two distinct yet equally critical stability problems solved through these elegant constraints.
What about the third major bottleneck they addressed, which impacts inference efficiency?
That's the memory wall, and they solved it with their custom attention mechanism, multi-head latent attention, MLA.
The memory wall relates to the KV cache, right?
Precisely. For the transformer to maintain context across long sequences, it stores the keys, K and values V, of all previous tokens in a memory structure called the KV cache. As the sequence length grows, the KV cache grows linearly. This quickly consumes prohibitive amounts of GPU memory during inference.
Which is why long context models are so expensive to run. So how does multi-head latent attention, MLA, break through this wall?
It uses a low-rank joint compression. Instead of caching the full key and value vectors for every single token, they are processed through a function that compresses them into a much smaller, shared, latent vector, CKBLA.
So it's like summarizing. Instead of storing every single sentence, you store a very high-quality, dense summary of the preceding information.
That's a great way to think about it. This low-rank approximation means the cache size no longer grows linearly with sequence length in the same way. The memory stored is the size of the compressed latent vector, which is constant. And related work showed that MLA could achieve a reduction in cache size of up to 98.6% per token.
That is astonishing. This entire effort, from the geometric constraint in MHC to the bias adjustment in MOE to the compression in MLA, all supported by kernel fusion and efficient scheduling, it really demonstrates a successful path. The complexity and capacity of models like DeepSeek V3 no longer require crippling efficiency and numerical instability.
And the proof is in the results. They managed to train DeepSeek V3 on an unprecedented 14.8 trillion tokens with remarkable stability. No irrecoverable loss spikes, no costly rollbacks, at a relatively contained cost. The success validates their integrated philosophy of seeking mathematical elegance alongside relentless system optimization.
Okay, let's synthesize this whole journey. The DeepSeek researchers, seeking greater capacity, introduced the hyperconnection, or HC, which broke the fundamental stability rule of ResNet by creating unbounded signal amplification.
The dead end was that HC delivered performance, but it invited chaos.
And the definitive solution, MHC, restored stability not by regressing back to simplicity, but by applying precise mathematical control.
They constrained the learned connection matrix to a specific geometric boundary, the doubly stochastic manifold, using the Sinkhorn-Knopp algorithm. And that act of constraint restored the conservation of the feature mean, allowing complexity and scalability to coexist.
The result is a system that confirms the power of innovation across all scales. Microarchitecture fixes like MHC, working in lockstep with system-level optimizations like kernel fusion, recomputing, and the dual pipe schedule. It shows that the future of massive AI is really rooted in this integrated engineering.
And what's perhaps most exciting is that this framework is incredibly flexible. The authors successfully used the doubly stochastic constraint, which is beautiful because of its closure property and mean conservation, but they explicitly anticipate that future research will explore diverse, manifold constraints.
So researchers might start experimenting with other mathematical constraints, other geometric shapes, tailored to specific, complex objectives, maybe prioritizing resilience to noise or optimizing for transfer learning capacity.
Exactly. They are trying to optimize the fundamental trade-off between plasticity, the network's ability to express complex, nuanced relationships, and stability, its ability to train effectively at scale. The double stochastic constraint is one excellent solution, but others are certainly out there.
This work has essentially rejuvenated community interest in macroarchitecture design. It shifts the focus away from just scaling up parameter count, which is kind of like just building a bigger box, to topologically restructuring those blocks to improve the underlying optimization landscape.
It's about designing a more intelligent internal communication structure.
Right. It illuminates a crucial pathway for the evolution of next-generation foundational architectures that have to balance massive capacity, high performance, and economic efficiency. The days of simply throwing compute at instability are, it seems, ending. Precision and mathematical elegance are now the drivers.
I think so.
We started by noting that the stability of the largest LLMs relies on a 10-year-old architectural trick, the residual connection. The DeepSeek AI story shows the human journey of innovation, challenging that trick, hitting a catastrophic wall of instability, and then being rescued by finding elegant geometric constraint.
It's a remarkable convergence of fields. The stability of the world's largest language models today depends not just on massive data and compute, but on an elegant 57-year-old mathematical theorem, the properties of doubly stochastic matrices, and the iterative projection of the Sinkhorn-Knopp algorithm used to impose order on architectural chaos.
That is a fascinating thought to take away. Our most complex machines are being tamed by the purest ideas from abstract mathematics, which raises a final provocative question for you, the learner. Given the success of the Birkhoff polytope in solving this scaling crisis, what other seemingly obscure or long-forgotten areas of pure mathematics, developed decades ago for entirely different reasons, hold the geometric keys to unlocking the next massive leap in stable, scalable intelligence? Where should researchers be looking next to find the geometric constraint that solves the next big crisis in AI scaling?
A powerful thought to consider. Thank you for joining us for the deep dive. We'll see you next time.
Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other podcasts, responding to the content, and checking out our related articles at helioxpodcast.substack.com.